Okay, so we're going to look at the problems that involve combustion analysis. So the first thing I want you to go ahead and write down in your notes is I want you to write how to burn a hydrocarbon, because that's what combustion analysis is going to be all about. It's burning a hydrocarbon. If we are in agreement that a hydrocarbon would be CXHY, and we're going to burn that hydrocarbon, so we have to put plus O2. And we will end up with carbon dioxide and water.
How to burn a hydrocarbon?
A hydrocarbon. How to burn a hydrocarbon. Does this look familiar in the types of reactions that we've done before?
Pretty sure.
Yes, Aisha? Yes, you may, Aisha. Thanks for asking. Okay, now let's look at the problem that they gave us to work with. Okay, one thing we don't know is we don't know these subscripts X and Y. We only know that this is a hydrocarbon and it contains carbon and hydrogen. Okay, so our job is to find those subscripts X and Y. So let me pull this back up. Okay, the information that we have given to us in the problem is that this hydrocarbon, we have 1.50 grams of it. So I want you to write that down underneath your hydrocarbon on your paper. Jot that down, 1.50 grams of your hydrocarbon. How much carbon dioxide did they say we have?
Carbon dioxide?
Carbon dioxide.
4.4.
4.40. And how much water do we have? 2.7 grams. Okay, so that's, you're writing this down, 2.7. You should be writing it down something like this.
Oh.
Okay, so when I say write it down underneath, yeah, that helps you keep up with things. If you'll go over and look over there. I'm not sure what you're asking me about, Reagan. What would it be, a dash or a dot in a number? Okay, so this is the information that they're giving us to work with, and our job is to find the empirical formula of our compound. Okay? Now, would everybody agree that all of our carbon wound up in one spot? It's all in the carbon dioxide. Would you guys agree with that?
Yes.
Okay. And where is all of the hydrogen located? It's located in the water. That's exactly right. Okay. I'm not real sure. I need to make sure I'm sharing my screen like I needed to. Okay. Okay. All right. So if we started off with our carbon dioxide, we could pull the carbon out of there, couldn't we? Okay. So let's start off with 4.40 grams of CO2. And it's in grams, so I got to get rid of grams and change it over to what? Moles. Okay. So those of you that had a little quick workshop yesterday, can you tell me how many grams per moles carbon dioxide is? Good. 44.01 grams in 1 mole of CO2. Now that'll just real quickly take us to moles, but we need to go to not moles of carbon dioxide, but moles of carbon. How many carbons are in there, in that carbon dioxide? Okay, good. 1 CO2 has 1 carbon in it. Okay, so don't skip that step, even though that's just a 1-to-1 ratio. It's important that you understand you're pulling the carbons out of the carbon dioxide. Okay, so real quickly, I want you to plug that into your calculator and let's find out how many moles of carbon that we have. Yes, sir.
Is the value in the combustion equation of oxygen, is that going to be a different coefficient depending on hydrogen?
Yeah, we don't know what that coefficient
so that's
is.
the reason why we need to another value of hydrocarbon.
We'll, yeah.
We'd be able to just take those two and then be able to tell.
We could figure out how much O2 we used in that. Yeah, we
Well, that's
could.
what I'm asking you.
Oh.
We didn't have the value of the hydrocarbons.
Right. Hang on. Let me make sure I'm answering. Let me make sure I'm answering Patrick's question. Okay, so go. It's the same question. So shoot that to me again.
Sure. So if you didn't know the value of the hydrocarbon,
Okay.
you could just subtract the oxygen. Right? Okay.
Yes.
And then you'd be able to extract the values of carbon. Right? If that O2 was only a no, it was never 3.
Right. Except the only thing is your oxygen. Yeah. So you know that's made up of carbon and hydrogen. I think you could do it this way. You could add these two numbers up, and that would give you how much oxygen would we have used in that reaction? Because law of conservation of matter. So 4.4 and 2.7 would be 7.1 total mass on this side, right? 7.1 minus 1.5 for the hydrocarbon is how much oxygen would be used. Okay, and so how much is that? We just subtract that real quick. 5.6. Okay, so is that similar to what we know how much oxygen is there. We know 5.6 is the mass of oxygen, but what we don't know is how much of this 1.5 grams is hydrogen and how much is carbon.
So do we need to find the oxygen?
No, we don't need to find the oxygen. I was just trying to answer Patrick's question, I think.
The thing is, you don't need that 1.5 to be able to do.
No, we don't need that on this problem. This right now, this number is irrelevant. You're exactly correct. It will become relevant as we're going to work one that I'll show you. It will become relevant. Okay. Right now, we're trying to figure out how many moles of carbon, and we will also need to know how many moles of hydrogen is in this hydrocarbon. We're trying to figure out that X and that Y. Okay. Okay. So now that we have established what we're looking for, what is the answer to the number of moles of carbon that we have here? 0.1. Let's go a little bit farther out in sig figs there, Patrick. You guys all should be calculating this with a calculator, plugging it into your calculator and coming up with a number. That would be good. 0.09. What's after that? 9. Okay, and let's go one more because this had 3 sig figs in it. 9. Okay. You good with that, Sandy? Okay. All right, now we got the carbon out. Let's pull the hydrogen out. Okay, same little setup that we're going to do, except realizing that all of our hydrogen is tied up in the water. So we're going to take our 2.70 grams of water. Okay, what's the first thing that we need to do?
Want the hydrogen? No, get the,
Molar mass of water, good. So for every 1 mole of H2O, we have some number of grams of H2O.
2.02 plus 16.
Plus. So 18.02, good. Okay, and then let's recognize the fact that in water, there is not 1 hydrogen, but there are 2 hydrogens for every 1 water. Is everybody good with that part? Okay, all right. So then let's real quickly figure out how many moles of hydrogen we have.
Okay.
True, but more or less than your carbon.
What am I doing?
So you're just you're multiplying by 2.7 times 2, divided by 18.02. Okay, so we're now to the step where we were yesterday. We're in moles. What are you going to do at this point? You've got moles.
By the smallest one.
Divide by the smallest, which is going to be the carbon, right?
Oh, that 0.0.
Yeah, it's 0.0.
Yeah, I forgot that.
Can you just round that down?
I mean, you can kind of see that's a 1-to-3 ratio, I guess, from there, can't you? Yeah. But it's always good to kind of check your work and make sure that it truly is a 1-to-3 ratio, just in case. So I believe we're going to get a 3 right there. Reagan, do you have a calculator now? Okay, are you calculating with us? Okay, so our last step, write your formula. So what's our formula going to look like? Okay, guys, this is question number 1. It's a 3. Sorry.
Oh, that's how you do that.
That's your answer. That's what you're looking for. Ma'am, that's number 1. That's number 1. Okay, Lindley, that's your empirical formula. They didn't ask for a molecular formula in this one. They just want to know, what is the empirical formula? Okay. All right, we're going to do one more together. And you've really got to pay attention to this one. Reagan, put that down. You're going to need to pay attention. Yes, except you've got oxygen in this next one. Okay. We're going to look at number 4. Number 4 is probably the most complicated one on this paper, so we'll work this one together, and then you can work the easier ones by yourselves. Girls, if you don't stop talking, you're both going to be with me after class, and we'll discuss what we're going to do after that. Do you understand what I'm saying? I've already moved you. You're going to stop having a private conversation. Okay, number 4 is all about caffeine. It says it's a stimulant found in coffee, tea, and certain drinks. It contains 4 different elements. It has carbon, hydrogen, oxygen, and nitrogen. Okay, so go ahead and I want you to write down your hydrocarbon. Say that again. Oh my gosh. Yes. I understand what you're saying. It's going to be in pretty much any tea that comes from tea leaves. It has caffeine in it, unless they've decaffeinated it. Okay, now let's write down all of our givens that we have. This hydrocarbon, which has CHO and N, so you've written down CHO and N, right? Underneath that, you have 1 milligram of it, mg. Okay, now this is going to be burned, so plus O2. Show you what I have written down so far.
Oh, okay, wow.
CHO and N plus O2. When we burn this, we're going to get carbon dioxide, water, and the nitrogen has to go somewhere. So this nitrogen is going to form N2.
How about FN?
Okay. Now let's get some numbers to put underneath those species. So I'm going to go back real quick. And the carbon dioxide is 1.813 milligrams. Water is 0.4639 milligrams. And nitrogen is 0.2885 milligrams. Let me scoot this over so if you didn't catch all those numbers, you can get those down. There you go.
Ah!
Are you okay?
No, it actually sparked and big shock my finger.
Sue the school.
Sue
They don't give money.
It could very well just be a little static electricity that
No,
you've
it
got
actually did.
extra. Yeah.
As soon as my
Right.
finger hit the file cabinet.
Okay, guys, to save us a step real quickly, notice these are all in milligrams. Let's just real quickly change all of these numbers to grams, and that's going to save you a lot of work in your process, okay? How would you change milligrams to grams? What would you need to? You would do what with 1,000? Multiply or divide by 1,000? That is the question. Multiply. Let's look at, there are 1,000 milligrams in 1 gram. So if you said divide by 1,000, you are correct. Okay, Okay.
You just made me second guess myself.
No, I thought I heard both, and so I'm just checking. So when we divide by all these numbers by 1,000, we're going to get some really small numbers. So I want you to go ahead and do that so that we don't have to put that into our process. Divide each one by 1,000, and we want to go ahead and get this in grams. Okay, that's why we're dividing this by 1,000. When you get your numbers, most of them are going to have e to the negative something.
Oh, that hurts.
Yeah,
so
can you
much.
just change the end product to grams instead of changing each individual thing?
I think you're going to need, I'm trying to tell you guys, you're going to need to go ahead and have it in
Wait,
grams. So.
divide by 1,000, which means you move
Okay.
the decimal back to the left 3 places. 2 places.
3 places.
You know what you do? Just put in 3 more zeros. Here's tough. I do. Because the calculator is easy. I don't want to do that math.
Or times 10 to the negative
I just write it-
third.
Yeah, I was just like, can I just write it in scientific notation?
Uh-huh. Yes,
Can I move?
please. Okay. It's just in scientific notation, just dividing it by 1,000. Okay. Yeah. Okay. Are we all there? The only reason I said that we're going to need to do this is because we have 4 elements in this compound, right? We only can find 1, 2, 3 from pulling them out of these numbers. We're going to have to get oxygen back out of this. So I'm going to show you how to do that. Okay, so let's go ahead and do the same process that we just did. Let's get our carbon, our hydrogen, and our nitrogen pulled out separately out of these masses that we're given. Okay, so the first one we have 1.813 times 10 to the negative third grams of carbon dioxide. I want to get the carbon out of that. So what am I going to do to get the carbon out of the carbon dioxide?
Same thing we just did in the last one.
Same thing we just did. So 1 mole CO2 for every, and you gentlemen should be writing this down as we're going, because I'm going to start getting faster and faster, and you're going to be crying that, yeah,
I'm already lost. So.
I'm already crying.
that I need to slow down. Well, I'm just saying, pay attention, okay?
It is. I just can't write fast.
Sammy, I'm not talking to you. Okay, so as soon as you get that written down, go ahead and do your calculation.
Do you use big E or small E to put it in your calculator?
Good question. I'm glad that you use the small, well, the EE is what you're using. You guys see where my finger is right here? It's on the comma. So we're going to put it in like this, 1.813 second comma, and that puts the E up on your screen. And then just hit -3. Okay, that E means times 10.
Oh,
Okay,
okay. How would you do that again?
second comma, Chloe.
Oh, okay.
Okay. And then we're dividing by 44.01. We good? Okay, let's do the same thing for hydrogen. Let's do the same thing for nitrogen. Hey guys, your concentration is 0.1, and there are 2 bottles that are sitting out on one of the middle tables. They're together, and it says sodium acetate, I think, on one, or it may say potassium acetate, and the other one is acetic acid, but its formula is not named. So the bottles are about this tall. Do what? Yeah, use the same pH. Okay, so for water, 18.02 is your molar mass in 1 moles in 1 mole. And then there are 2 hydrogens for every 1 water. Okay, let's get your numbers done real quickly on that one. I like the 2.57. That's probably, so 2 sig fig, or 3 sig figs there. 2.57 times 10 to the negative 5th. Okay.
Oh.
So she needs a different mantissa.
A lot.
That's what that front number's called.
Yeah. Okay, so you multiply by 2.
Yeah. Okay. So 5.15 times 10 to the negative 4th. Did I do that right? Okay. Mantissa. Okay. Oh, you know what, guys? I messed up. Go back and look. Where did I mess up?
Oh.
I messed up in the hydrogen right here. This should be a -4. And that should be a -4 for our grams. Because look, if I move my decimal point over 3 spaces, boom, boom, boom. I mean, wait. Hang on. I'm dividing by 1,000, right? Moving my decimal place over 3 spaces this way. And put that in scientific notation, that would be to the -4th, not the -3rd. Mm-hmm. Yeah. Yeah, that's to the -4th. Okay, which is going to change this now to the -5th. There we go. That's all that's going to change. The rest of that's fine. We just needed 1 more decimal place. Okay. Okay, last one that we have that we can work with. Starting off with your nitrogen, we've got 2.885 times 10 to the -4th grams of N2. Okay, and so for our molar mass of N2, that's 28.02 grams in 1 mole. And then that is 2 N's in every 1 molecule of N2. Y'all understand where we got the numbers on that? Yes? Okay. So I got 2.06 times 10 to the -5th, and this is going to be moles of nitrogen. Make sure you're okay with that number before we move on.
Why would we not use 460?
We should, to be honest with you, Hannah. We should. So I probably should. I'm going to leave it right there so I don't have to cross mine out. But on your paper, do that.
So for 4, would it be 2.2592?
On which one?
For the 460 for nitrogen.
I would put it as 2.059. It would just be 2.059, not the 2. Yeah. All right, guys, we have everything we need except for the oxygen, right? So that's the only one that's hard. We could like say if this only had carbon, hydrogen, and nitrogen, we would divide by the smallest at this point and we would be done. But we've got the oxygen that's going to cause us a little bit of a problem, okay? Oxygen is in two different things and it comes from two different places in our equation, right? So we do have something that we're going to use though. We have the mass of our hydrocarbon, right? And if we already know the moles of carbon, the moles of hydrogen, and the moles of nitrogen, if we converted all those moles to grams, couldn't we subtract them from that original mass to get the mass of oxygen? We could do that. So don't let go of your mole numbers because you're going to need them, but just down a little bit farther on your paper, I want you to just simply convert those over to grams real fast. So for carbon, we've got 4.12 times 10 to the negative fifth moles times the molar mass of carbon, 12.01 grams per mole. Do the same thing for your hydrogen and do the same thing for your nitrogen.
Where did that 4.12 come from?
I believe I got it from the carbon.
Oh.
Yeah, that's carbon's mass and or moles. And then I'm going ahead and plugging in my hydrogen. Malcolm, when you get the first one, tell us what you get for grams of nitrogen, of carbon, grams of carbon. What is it? What we got going on here, right here? That's a time sign. So take your front number, multiply by 12.01. Hannah, would you get hydrogens real quickly? And Lindley, would you get nitrogen's number real quickly? Okay, so you got 4.94 times 10 to the negative fourth. Okay, and that's for carbon. You know, when you get yours, just call it out.
5.21
Negative 5. Okay, and this is grams of hydrogen.
Wouldn't it be 5.202?
They can only go to 3.
Because it's 2015, so the 1 round to a 2. And, oh yeah, that is like 5.202.
Okay. Here, I'm gonna have to rewrite.
Ooh.
All right, and then Lindley, what do you have for the last one?
2.89.
And that would be grams of nitrogen. Okay, so we've got everything converted back to grams. Now, add those numbers up. Okay, and you're going to subtract from your original mass of your hydrocarbon to get how much oxygen is in there.
Weren't those original numbers already in grams because we converted from milligrams to grams? So your answer would be in grams?
No, that was of carbon dioxide, water, and nitrogen, not of carbon, hydrogen, and nitrogen. Okay. Yeah, that's why we had to do that. Because we had to pull the carbon out of the carbon dioxide. We had to pull the nitrogen out of the N2 and the same way for the hydrogen out of the water. Okay.
So you subtract it by the after you divide it by 1,000? Of the oxygen.
Yeah, because these are all grams, right? Okay, so remember when you add or subtract, you have to have the same units. And so that's why I wanted you to go ahead and convert everything. Can't see that. I wanted you to go convert everything in grams, and that way you're going to just subtract. Just find out how much oxygen you have. Okay, so I'm going to add these numbers up. Everybody do that. Add your numbers up if you haven't done it. You're adding up your grams of your species that are not oxygen. So add your carbon, add your hydrogen, add your nitrogen up. Yes. So this is giving me 8.36 times 10 to the negative fourth. And then I'm going to subtract 0.001 minus that number. And that should be our mass of oxygen.
I got a negative number.
You shouldn't get a negative number.
Negative 0.001.
Yeah, it's 0.001 minus 8.36 times 10 to the negative fourth.
Oh, well, I just like subtracted it from 8, so that's probably why I got a negative number.
Right. So which one's your bigger number? What's the bigger number would be our hydrocarbon, right? That number is 1 times 10 to the negative third. Okay, and so if you got a negative number, just take the negative sign off if that's how you plugged it into your calculator. So our mass of oxygen, okay, so 0.001 minus all the carbon, the hydrogen, and the nitrogen gives us the mass of just the oxygen, grams of O. So I got one, go ahead, Haven. Who asked me? Okay. 1.6. I'm just going to round it to a 4. Okay, is that all right with you guys?
It would round up to 5.
Okay, we'll call it a 5. All right, so 1.65 times 10 to the negative fourth will be our grams of oxygen. And then what are we going to need to do with that before we can do our empirical formula? We're in grams,
Yes.
so divide by the molar mass, find moles. Okay, so we're not yet ready to divide by the smallest. This is in grams. We need to convert this to moles. 1.65 times 10 to the negative fourth. Shh, Malcolm, stop. Just talking like about, I don't know what. Let's get this let's finish this problem.
I don't even know where space.
Go to the next page.
You gotta hold up to it.
That's right. This number right here. Okay, back it up and let's look at this. Where did this number come from, Jasmine? That's everything, right? That's carbon, hydrogen, oxygen, and nitrogen. So if you subtract out the carbon, the hydrogen, and nitrogen, you get just the mass of the oxygen. Okay, so I've just subtracted that original amount that had everything in it. We'll just go ahead and write C, H, N, and O. That had all 4 pieces in. Subtract 3 of the pieces, and you get the 1. Okay? All right, so then let's go ahead and finish converting this into moles. And when we divide that number by 16, I got 1.02 times 10 to the negative fifth. And that's going to be in moles of oxygen. That's not what my calculator says, but if you want O3, I will put O3 in there.
There's a 1 after the 3.
Because I just used what was in my calculator. So if you want a 3, I'm going to put a 3.
So when you're dividing by the smallest, you don't have to put e to the negative fifth because they're all e to the negative fifth.
That is correct. Very good, Aisha. Very good. Okay, so now we are ready to actually come up with our empirical formula, right? Got everything in moles. That's what we need. So looking for your smallest number. Here's our oxygen and our nitrogen, our hydrogen, and our carbon. Which of those 4 numbers is the smallest?
Oxy.
The oxygen. So we're going to divide everything by the oxygen. And like Aisha said, look at all your exponents. They're all times 10 to the negative fifth, right? So we can just ignore that part and we can just divide everything by 1.03 I'm not going to put that times 10 to the negative fifth in my calculator. Make things a lot faster. So auction's value is going to be a 1. Y'all with me on that? Auction's value would be a 1. That's the smallest. Okay, how about nitrogen's value? A 2, good. And how about hydrogen's number?
5.
A 5. And carbon looks like it's going to be a 4. There we go. Okay, so we have enough information now. We have our numbers. Let's write our empirical formula. We've got C. Perfect. On carbon, a 4. Did they ask us? They said to estimate. So
No, I think it's like it could be. Also, you can divide that by.
Okay, so if you wanted to see what its molecular formula, it says it's going to be from what, 150 to 200, I think is what the problem said. It says to estimate the molar mass.
We didn't have to.
Right. So it says to estimate it's supposed to be. So let's find out what our empirical formula mass is real quick. So you got 4 carbons, 5 hydrogens, 2 nitrogens, 1 oxygen. I want everybody, add those up and add up all your molar masses for this and find what that is. 4 carbons, 5 hydrogens, 2 nitrogens, 1 oxygen. Add those up and see what empirical formula mass you get. If y'all agree with Patrick,
Well, I screwed up too.
don't quit.
What do you say?
He said 97.11, but let's see if you agree with him. Carbon, and you can estimate, carbon weighs what? Like 12. Hydrogen weighs 1. That weighs 14, that weighs 16, right? Okay, so just 2 nitrogens, yes, sir.
16. Oh, no.
Sorry, let me pull this up so you can see it.
Nitrogen is 20.
97.1. Okay, so if our molar mass is supposed to be between 150 and 200, what would you anticipate we would need to multiply our empirical formula by if the empirical formula mass is 97.11 times 2? That's right. So our molecular formula would be, what would our molecular formula be?
8, 10, and 4, and then
Nice. Okie doke. All right. Yes, ma'am. That's what they actually said in our problem. They said that your molecular formula mass is estimated to be between 150 and 200. So, yeah, if you multiply 97.11 times 2, you could see it would fall in that range. Yeah. So that way it gave us something to work with. You know, it's like we got to keep it between here. So, you know, it's not going to be just that. It's not going to be our empirical formula. It's going to be that times 2. We keep it in that ballpark range. Okay, goodness gracious. That was a long problem. That's probably the longest problem on here. So I'm going to give you the remainder of the time to look at these, to actually work the rest of those problems on that page. Okay, you've got 2 examples to look at, to go back and help each other out with. I need to see, who do I need to see? Sammy, I need to talk to you. Shepard is not in this class. Xander, Mary, and Dave. You guys come talk to me real quick, okay?
That's what I'm saying.
Yes. There's some tissue right over there, and just go in the hall. Okay. All right, guys. Yeah. So if you do better than you did last time, you get 5 extra points. Okay. All right. So I'm just saying, give it your best. Okay. 5 extra points. Yeah. Unless you need to get one of these. No, you got a couple of examples there. So. maybe one of the hardest ones.
I've always done that.
Number 4 was the hardest one. Just took the most. I mean, we could have
It's just not
probably
solo
gotten there in a
stuff.
different way, but I have to get the
did.
I want to find a different way
Yeah.
because I don't know why, but I hate the like drip line with the.
You
You
always
don't like it?
choose
That's fine. That's fine. It's not everybody's favorite. Okay, so you guys, do you want to go in the lab? And just your computer charge.
Now what do we work on?
So you'll just go in the lab and you just take readings. Okay? Alright, be really careful if you're climbing under. Because this, I have to take really good
I
care
don't
of.
know why, but I hate that thing. So I'll
Okay.
find something else.
Okay, all right, you're good to go if you need to.
Yes, I'll come back in.
Yeah, come back. Okay, Trinity. Actually, we're just gonna attach it to today's stuff. So